Okay, so we are going to start problem number 4. Okay, so what does problem number 4 say? It says that there are two charges fixed, let me draw the figure first. This is problem number 4. There are actually two charges of plus q fixed at points A and B. So these are the charges. This is plus of q, and this is also plus of q fixed at points A and B, which are at a distance twice L apart. So let this be your origin O. So this is of a distance L, and similarly this is of a distance L, and in this horizontal plane, let me also consider this horizontal plane as well. It's X and Y. Okay. So the center means the center of a mass of a rod of length 2L is free to move along the x-axis in the horizontal plane. So this is also a length of a rod of length 2L, which is constrained to move along the center of mass of which is constrained to move along the x-axis in a horizontal plane. So let me draw the charges. This is plus of q, and this is minus of q. Okay, and it is free to rotate about an axis perpendicular to the xy plane. So the axis of rotation points along the z direction, and for the first part of the problem asks you to find the constraints of motion and hence find the degrees of freedom. So your system is actually these two charges, because this one and this one are fixed. So your system under consideration are these two charges, plus of small q and minus of small q. So let me just denote the coordinates of plus of q be x1, x2 and x3. Okay, similarly let me denote the coordinates of minus of q. The coordinates of minus of q are designated as let's say x prime 1, x prime 2, x prime 3. Okay, so let us list down the constraints of the system. Okay, so the constraints of the system are, number 1 is that the entire system is constrained to move along the xy plane. So the first constraint that you can easily verify for yourself is that x3 is equals to 0 and x prime of 3 is equals to 0. Okay, now the rod which connects the plus small q and minus of small q is a rigid rod. So the rod is rigid. So what it means to be rigid is that the distance between the points plus q and minus of q is fixed. So from that we can generate our third constraint, which is the root over of x1 minus of x prime 1 whole square plus of x2 minus of x2 prime whole square plus of x3 minus of x prime 3 whole square is equals to basically the length 2L of the rigid rod. So this is your the third constraint. And what is the fourth constraint? The fourth constraint says that the center of mass of this rod of length 2L is actually constrained to move on the the x-axis only. So what are the center of mass coordinates? The center of mass coordinates are x1 plus of x prime 1 divided by 2, comma x2 plus of x prime of 2 divided by 2, and x3 plus of x prime 3 divided by 2. But you already know from the first and the second constraints that x3 and x prime 3 are equals to 0, so it generates no new constraint. So this condition is that the center of mass is constrained to move only on the x-axis. So x3 plus of x prime 3 divided by 2 is equals to 0. It does not generate any new constraint, because you already have from the constraint number 1 and 2 that x3 and x prime 3 are equals to 0. But this thing which is that the center of mass is constrained to move only in the x-axis, this implies that x2 plus of x prime 2 divided by 2 is actually equals to 0. So this generates our fourth constraint. So now you started out with coordinates x1, x2, x3 for the charge plus q, and x prime 1, x prime 2 and x prime 3 for the charge minus of q. From this you have actually quantified 4 number of constraints. So out of these 6 coordinates, 4 of them are actually not independent and only 2 coordinates are independent. Then from this you can quantify that the number of independent coordinates is equals to 2. Now you can easily check for yourself, and you can easily also understand that you can quantify the coordinates of the plus q and minus q by by 2 independent coordinates. One of them would be the distance from the origin to the center of mass, which is given by x, and since this length is L and this length is also small l, the another coordinate that you require is just theta. So x and theta will completely quantify or give you the position vector of the charges plus q and minus of q. Okay, so this completes the first part of the problem. Okay, now you have to find out the potential energy of the rod if the center of mass is at a distance of x from the origin and it makes a certain angle theta with respect to the positive y-axis. Okay, so let me just draw the configuration here once again. Q and plus of q, and from the center you have the x-axis, this is q and this is minus of q. This makes an angle theta. This is the position A, this is position B. Let them be coordinates, for example P, and let this be Q. So obviously what you have to find out is that the coordinates of you have to just find out these distances for the potential energy. So first of all, let us find the distance. Let's say let us find AQ. Okay, so AQ is just, as you can easily verify, because now, okay, before that let me just quantify the coordinates. Okay, the coordinates of the charge plus q at A is equals to 0, L, 0. The coordinates of capital Q at B is equals to 0, minus of L, 0. Now the coordinates of the charge plus q at the point capital Q is equals to x plus of L cos theta, L sin theta, 0. Similarly, the coordinates of minus of q at the point capital P is equals to x minus of L cos theta, minus of L sin theta, 0. From this you can easily verify for yourself. It's just a simple calculation of finding out the distance. So the first point AQ is given by root over of, this is actually a very bad diagram, root over of L minus of small l cos theta whole square plus of x plus of L sin theta whole square. Now the distance AP is given by L plus of L cos theta whole square plus of x minus of L sin theta whole square. Similarly, you can verify that the distance BQ is given by root over of L plus of this will be capital L plus of L cos theta whole square plus of x plus of L sin theta whole square. And similarly, the distance BP is given by root over of L minus of L cos theta whole square plus of x minus of L sin theta whole square. And obviously the potential energy of the configuration U is equals to, you know, minus of Q into Q divided by 4 pi epsilon naught times of 1 by AQ plus of 1 by AP plus of 1 by BQ plus of 1 by BP. So this is your potential, and the potential energy of the configuration. Okay, the electrostatic potential energy, they obviously we are ignoring any gravitational potential energy or whatsoever. So this concludes the second part of the problem, that is finding out the potential energy of the configuration. And the third part is just the limits of just the limits of finding out the potential energy of the configuration under the limits that L is much greater than small l, L is much greater than small x, and theta is much less than 1. So all you have to do, and this is just simple algebra to proceed, and I'm just going to skip this part as an exercise, because you just have to binomially expand everything in terms of small l by capital L, small x by capital L, and then you have to use the Taylor series or the Maclaurin expansion of cos theta and sin theta. Okay, cos theta Maclaurin expansion goes like goes like 1 minus of theta square by 2 plus of theta to the power 4 by 2 factor plus of theta to the power 4 by 4 factorial, plus higher order terms. Similarly, sin theta Maclaurin expansion goes like theta minus of theta cube divided by 3 factorial plus of the higher order terms. So you just have to use these expansions for cos theta and sin theta. Similarly, binomially expand in terms of small l by capital L and small x by capital X, and neglect higher order terms. Carry over this analysis to everything. All these are terms of perturbation. Let this be epsilon, which is much less than 1. Let this be some lambda, which is much less than 1, and similarly theta is also much less than 1. So in these limits of theta, epsilon, lambda and theta much less than 1, binomially expand and Taylor series expand each terms to second order powers, okay, and neglect higher order terms which are greater than second order. And if you do this, you will find that the potential energy under this under this limit of small l by capital L much greater than 1, x by L much less than 1, and theta much less than 1. Under these conditions, you can find that the potential energy of the configuration approximates to minus of twice of capital Q by small q divided by 4 pi epsilon naught into L into twice minus of x square plus of L square theta square divided by L square. So this is just a simple exercise that you guys have to carry out of Taylor series expanding and everything. Okay, so this concludes the problem number 4. So let us go ahead and do problem number 5. Okay, so what does problem number 5 say? The problem number 5 says that a block of mass m is tied with 2 springs of length L, and the spring constant is K, and it is held on a frictionless horizontal table. Okay, the other end of the spring is fixed on the horizontal table, and the block is then displaced by an amount x in the perpendicular direction. Okay, so let me just draw it for convenience. So there is this spring, and this is the block of mass m. The spring constant is K, and the the equilibrium lengths are capital N, capital L on both sides when it is in an equilibrium position. Now what it is done is that the block is displaced by an amount x in the horizontal direction. Let this be the displaced position. That is why the springs will get elongated or extended, and you have to find out the extension in the spring by which from the mean equilibrium position. Okay, so this length is x, this is the same block of mass m, this is your x axis and this is your y axis. So you have to find out the potential energy of the block for this configuration. So it's very simple. You have to just find out the length of this part of the spring. So the length is obviously L square plus of x square. This length under the extension is also L square plus of x square. So the extension of the spring in both these sides. So the extension in this part is, let me denote it by delta x1. Delta x1 is obviously L square plus of x square minus of L, and similarly the extension in this part, which is delta x2, let me denote delta x2 as again the same quantity, L square plus of x square minus of L. Obviously under these extensions the potential energy of the spring is half of k delta x1 square plus of half of k delta x2 square, and it's pretty straightforward to do the calculation and show that the potential energy of the configuration under this extension of the springs is just k of root over of L square plus of x square minus of L square. And mind you that there is no gravity. I mean, since gravity is pointing downwards or perpendicular to the horizontal plane, so there is no a potential energy due to the configuration due to gravity of the configuration due to gravity. So this is the potential energy that is the potential energy of the configuration due to the extension of the springs. Let me write this in one another form. This is just k of you can take L outside, and you can just write that this will be okay, I made a small mistake. This shouldn't be L square, but this should be just L. Did I make the same mistake? No. Okay, so this is just that. So we can take L outside and write this as 1 plus of x square by L square to the power half minus of L. So this will be equals to okay, so there should be a square. I'm making quite a bit mistakes over here. There should be square because obviously these are squared quantities. I'm sorry for these goof ups, but these are squared quantities, so obviously these should be there. Good enough. So this is equals to k L square into 1 plus of x square by L square to the power half of minus of 1. So this is your potential energy that is stored. I mean, this is not stored actually, the potential energy of the configuration as a result of the the extension of the springs. 1 plus of x square by L square to the power of half minus of 1. Good enough. So this concludes the first part of the problem. The second part of the problem says that for a small displacement, that is x much less than L, will the block exhibit simple harmonic motion? So it's again just you have to calculate the potential energy in the limit x by L much less than 1, and you should just have to binomially expand this term. If you binomially expand this term, that this will be equals to k L square into 1. This will be equals to 1 plus of half of x square by L square minus of 1 plus of higher order terms, which will be x to the power 4 by L to the power L to the power 4. So your 1 and 1 cancels out, and your potential energy under this limit of x by L is much less than 1, is just k L square into this is equals to half. Again I am missing the same factor, that I have missed the squares over here. Please forgive me for my goof ups. So x square plus of L square whole square. So this is, so the potential energy plus of higher order terms, which are of the order of x to the power 4 by L to the power 4 whole square. So the potential energy in can be approximated in this limit as 1 by 4 k L square into x to the power 4 by L to the power 4. So this is equals to k x to the power 4 divided by 4 L square, or something like k by 4 L square x to the power 4. So your potential energy in the limit of x much less than L, or x x by L much less than 1, is given by something that is proportional to x to the power 4. So obviously you can compute the force, the restoring force in this case, which is equals to given by the negative gradient of u, and you will find that it is given by minus of k by 4 L square del x of x to the power 4 of x cap, which will be obviously proportional to x's cube, minus of x's cube by x cap, points in the for example in the towards the center. So this is indeed a restoring force, but this restoring force is not proportional to minus of kx. So obviously it will not be a simple harmonic motion. But the question is, is this a periodic motion, right? So will it still, even under this kind of potential, the mass m will still exhibit a periodic motion, and this is quite evident from the nature of the potential. The nature of the potential goes like x to the power 4, where the constant in front is just k by 4 L square, which is obviously greater than 1. This is a positive quantity. So the mass small m is actually undergoing periodic motion in the potential, something in the potential of something like let me be exact, k by 4 L square x to the power 4. Okay, one exercise that you can extend over to this is that under the periodic motion, in a periodic motion under a potential of kind which goes like x to the power 4, you can actually go and verify that the period of oscillation, even though it is not simple harmonic oscillation, but the period of this periodic motion is actually inversely proportional to the amplitude of the oscillation. And I'll just, for your curiosity, extend this problem to this part. But as of yet the tutorial is over, in that sense that we have calculated the potential. So what we'll do is just we'll work out this problem, that is we'll find out the time period of oscillation under the potential under the potential u is equals to some a x to the power 4, where a is obviously greater than 0. Okay, good. So how do we do that? So obviously since it is again a periodic motion, let the amplitude be a. Okay, so since the energy conservation applies in this, since there are no external forces at the turning points, that is when the mass is at a maximum distance, that is it is at its turning point, then the potential the potential energy or the total energy will be equals to a. I should not have used a here because I'm already using a's here, so let me use x max. So it will be equals to x max whole square. So this is your energy, because at the turning points the energy is totally potential and there is no kinetic energy. Okay, but at some intermediate point in the time period of oscillation, the kinetic energy will be equals to half of mx dot square, and the potential energy will be given by a into x to the power 4. Again I'm making some goof ups, this is x max to the power 4, I'm sorry for that. So this is your kinetic energy, and the potential energy at a particular position x will be given by a into x to the power 4. So your T plus of V is actually the energy of the system, and so half of mx dot square plus of a into x to the power 4, and since the energy is conserved, it is equals to a into x max to the power 4. So from this you can find out that half of mx dot square is equals to a into x max to the power 4 minus of x to the power 4. So your x dot square is equals to twice of a by m into x max to the power 4 by minus of x to the power 4, and so your x dot is equals to root over of twice of a by m into x max to the power 4 minus of x to the power 4 by to the power half. So this dx dt is equals to root over of twice a by m into x max to the power 4 minus of x to the power 4 to the power half. So your dt by dx is equals to root over of m by twice of a into x max to the power 4 minus of x to the power 4 to the power of minus of half. Good enough. So your dt is equals to root over of, let me just go ahead with the calculations and let me not say anything more. So now what we do is we calculate the time period. Okay, so you have the block of mass m under the in the limit of x by L, in the limit of x by L much greater than much less than 1, it is of the potential energy of the configuration in this limit goes like a into x to the power of 4, and we are trying to find out the time period. So let this be the equilibrium position, and it extends over till its maximum, which is x max, at which position all its energy is potential and there is no kinetic energy. At the equilibrium position, let this be the time t, and the time it takes to go from this equilibrium position to the maximum extension or the turning point, which is at its position of maximum extension, that is the amplitude. Let this be t, or let me just denote it as t. So the integration limits are from dt is equals to 0 to t, and obviously the integration limits of dx are from 0 to x max. And what is the integrand? It is equals to this particular thing, x max to the power 4 minus of x to the power 4. Okay. Good. So let us proceed with the calculation. So this is equals to 0 to x max times dx divided by m by twice of a, and we can just factor this out as x max whole square into root over of 1 minus of x to the power 4 by x max to the power of 4. This is just a simple simple algebra. Now we just do a change of variables. Okay, we go from x to y, where y is equals to x by x max. Okay, so obviously your dy is equals to dx by x max. Okay, and so your dx is equals to dy times of x max. Good enough. So so your x is actually equals to y times x max. So when your x has the value 0, okay, so when you, okay, let me just do it more clearly in this sense. So when your x assumes the value 0, y is also equals to 0, and when your x assumes the value of x max, y is equals to 1. So these are now the limits of integration. Okay, so what we have done is that we have just changed the integral by a substitution from d to t is equals to from 0 to 1 dx is equals to dy times x max times of m by twice of a into 1 by x max whole square into 1 divided by root over of 1 minus of y to the power of 4. So what you can find, that this is just the time period, this is just the time taken to go from the mean position to the point of maximum extension, that is the amplitude of x max. So t is actually equals to root over of m by twice of a. There is x max over here, and this is x max square, so this is equals to 1 by x max times dy from 0 to 1 of 1 by root over of 1 minus of y to the power of 4. So you just have to evaluate this integral, but whatever be this integral, you can find out that this is a finite number, right? This is just a finite number. So this is just a number, a finite number. It is obviously not divergent, which you can, since this is not, this is a well-defined integral because the limits are from 0 to 1, and so it is nowhere divergent. So this is just a, so whatever value this integral assumes is just a finite number. So let me denote this number by some k. Okay, so the value of this integral, whatever it will be, is that t in this limit of small x by L much less than 1 under the potential capital A x to the power 4 is equals to m by twice of a times 1 by x max into k. So you can see, but obviously you have to calculate, obviously you have to find out the the period of oscillation. We have just computed t, that is going from here to x max, that is time t, then it will go back, retrace the path, then again go through a distance from 0 to minus of x max, and then again come back. So the total time period is actually 4t. So you can calculate that 4t, which is the time period tau, that is the time period, is equivalent to 4 times of m by twice of a times kappa into x max. So the main point of the thing was to show that the time period is actually inversely proportional to the amplitude. Now why am I saying is this, that for the potentials going like x to the power 4, the time period is inversely proportional to the amplitude. For potentials like the simple harmonic motion, like potentials going like going like x square, the time period of oscillation is actually independent of the amplitude. So that, for this potentials going like x square, the time period is independent of the amplitude. So this concludes our discussion of problem number 4 and 5. If you have any queries, put them in the comments section, or any comments and criticism, it will be gratefully accepted. Thank you.